Okay. Could you please let me know if you can hear me? Just having a little rain check before starting. Awesome. This way, I also know how many of you are here in the stream. I guess we'll wait for like 1 more minute or 2 more minutes and then we'll start in case there are other people who are waiting to join in. Cool, cool, awesome, awesome. Let's do this. I have to admit, I'm actually a bit excited about this and a bit anxious about this because I don't know how it is going to work out. As yeah, I am going to be solving problems at first sight. There's a lot of things that could go wrong and a lot of ways I could get embarrassed. I was thinking to also like implement problems, not only discuss their solution. I guess one good thing to do is to actually grab some paper in case I will need. Cool. Let me know if you can see this. I was thinking of like, let's just, actually this doesn't work. Let's go to temp and test.cpp. Let me know if you can clearly see this, if this is okay for you. You might want to see it on full screen to like see the code. I will just wait for your like thumbs up or thumbs down. What difficulty? Well, I was thinking, well, I don't want to solve simple problems. I also don't want to solve really difficult problems, at least in the first stream, because I am a bit worried that I might just waste a lot of time, basically, not being able to solve problems. The idea would be to solve kind of Div1 ABC level difficulty. So that's kind of the main goal that I want to do. Like, okay, I'm glad that you like that I use Vim. I don't use Vim always. Like, I don't always use Vim, but if source code is short enough, I would probably stick with Vim, as it's very, I don't know, it's very simple to integrate it with the terminal and compiling and stuff like that. So let's see, let's do other live. Let's go to live, and here let's do a live one. Let's see. Close the update notification. Thank you. Okay. Cool. Okay, so in case you don't know how this is going to work out, I basically have a link to a poll, and I will be picking problems basically off of this poll, also of the comments on Code Forces on my blog. So if you want, I don't know, you can read the problems beforehand. These should all be problems that I haven't solved before, that I haven't seen before. And yeah, you can read the problems beforehand. I was thinking of keeping the statement on the left and like the code on the right, so that somebody who would join in at some moment during the live stream would be able to also see what problem I will be working on. We'll see how this will all work out in the end. Now, yeah, the main idea would be that I would start solving problems that are most voted. The most voted option here does not quite fit the the idea of a problem link. So I guess we might start with any Div2 round EF problem on code forces. Now, I'm not sure how I'm going to do that. I think like if you have a problem in mind that is Div2 round E or F and you want to see me try to solve it, just post in the comments now. If not, I'm going to just pick a random problem. So I'll just go to, I guess, problem set and look for things that have letter E and are not solved by very few. So it's Div2 and not Div1. I'm not sure if I'll be able to search, like I'll just go to a random page and pick a problem. So if you guys want any specific, if you're thinking of any specific Div2 D or E problem, just let me know now in the comments. I will just wait for like one more minute. The stream has a little bit of delay, so it might take some time until I catch what you will comment. I might change it in the future. So like I've seen that YouTube has some features that you can opt for low latency instead of quality. I opted for quality for this stream, but we'll see in case we will make more of them, hopefully. So yeah, I think I'm going to be waiting until like, I don't know, one more minute from now and look for your comments. If not, I'm going to be picking one random div2 D/E problem. I might do even both. I don't know. Cool. Says tags. I have to. Cool. Okay, I think the best thing is to just start with a random problem so that I will kind of get the hang of it. So I was thinking of this problem. It seems to be pretty random. It also seems to be like 2300 difficulty. I'm not sure what this is because like I'm not very sure about the difficulty on Code Forces problem, but it seems to be solved by quite some people. So I hope it will not be too hard. So the problem is called 013. Now to access this problem, you can go to, so it's contest code 1156/problem D. So it will always be here, like the problem statement. So first thing that I usually do is I just go over the problem statement, kind of read it. We're given a tree. Cool. Number is either 0 or 1. Traversing, we never go to 0 edge after going through 1 edge. Okay, so obviously constraints suggest that we want to do something that is subquadratic. So either big O of n or big O of n log n. And we are given a tree. Each edge is either 0 or 1. And we want to count some pairs of vertices so that from the path from x to y, there's no 0 edge after 1 edge. So because it's on a tree, it's kind of easier because by the fact that it's on a tree, there is only one path between two nodes. So let's see on this example. I guess so. The first thing that I notice here is that it's kind of hard to actually to actually enumerate all the pairs just by looking at the examples, so I won't be doing that. In some problems, I might experiment a little bit more on the example. So let's actually look here. So we want from X to Y to never go through a 0 edge after going through a 1 edge. So the idea is that a bad path, I'm drawing something, 0 edge, so let's actually, I have, you won't like this, but okay. So the idea is the thing that I'm kind of looking into is that if you have X and Y, like the ends of the path should look like this, because the idea is that you don't want to have a 0 after a 1. So you might have a prefix of 0 and then some ones. So it's kind of like increasing order, but you only have 0 and 1. Also, these paths are kind of valid as well. So having only ones and having only zeros. So this is also okay. But having 0 after 1 is banned. So kind of like once, oh, yeah, let's, it is a bit hard because like I have to look so that you can actually see. So these are all valid paths. Sorry for not showing you this. Okay, these are all valid paths. So the idea is once you get to 1, you won't be able to, you don't get to 0 anymore. So let's see how we would code this. So we want paths that have 0, 1. What I'm thinking that it, so we can see that we kind of have a special vertex, and I'm thinking of using this if this works. One idea, probably not the easiest, is that you can just have this vertex be like the important one, like each path has one vertex in which it gets switched from 0 to 1. And the idea of counting paths that look like this kind of boils down to counting, like for each node like this, count all the paths that have this node as the important one, like the switchover one. And if I have this, then it's kind of like counting how many paths full of zeros end in this node and how many paths full of ones begin on this node and go there. So like if I have something like this, paths of 1, it's you would just have to multiply the fact that I have, I don't know, 1, 2, 3 paths here, and then 2 paths here, and then 2 paths here, and add them all together, and then multiply it with the zeros, because like each path of zeros corresponds with each path of ones. How do we code this now? Okay, how do we code this? Let's, oops. So we do first problem. Let's call it P1 CPP. Let's code some easy, oops. Cool. And now let's, this is just some template that I like to code it beforehand on any contest. Like I don't have a template, so I just think that this does the job for me. So we have to read n. So let's do it, and then for each, so n minus 1 times, we will read okay, we'll read an edge. These are numbered from 1. Oh. Okay. So it seems like, I'm sorry, I'm not the greatest at this. So I seem to have been on the other. Okay, it's my face. Switch to screen, please. Okay. one thing that I will do probably for the next stream is that I will have an extra monitor so that I will actually watch the stream while I do stuff. Okay, so in place, back, AC, and now we have the graph. So let's think about it. Basically, we have paths of 0 and 1. And now for a node, we have to calculate how many paths of 0, like if you go only on edges of 0, to how many nodes you can get, and if you go only on edges of 1, to how many nodes you can get, and then just multiply it for each node. So the thing is, like, I started here with the graph that has basically for each node, it's adjacency list with like the cost to it to the edge, but I'm actually thinking of that it's better to just have two completely separate graphs, and basically the number of paths from one node to the other just corresponds to the number of nodes that it's in the connected component. So here, if you think about it, if you have I will not change it because I will forget to change it back. So here, if you have a 0, you can imagine that this is in one graph. So if you think about it, just considering edges of 1, the answer for this node for ones is actually the number of vertices in its connected component. So I could just keep two graphs. So let's do vector, 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 int graph. So we'll do graph assign 2. So we have two graphs, and vector, vector, int of n. So two empty graphs basically. And now I have the two graphs, and for each node, we calculate the size of the connected component for like the both of the graphs, and we'll just multiply it. So how would we do that? Let's see. We'll just do if the node is not visited. So let's see, if is not visited in 0, then we'll do a DFS on graph of 0, or like 0 maybe, starting with node I to compute the size of its connected component. And if it's not visited in graph 1, we'll do a DFS on graph 1 starting with vertex I. So what we'll also have to do is we'll have to have a visited array. So that would be a vector bool. Maybe it would have been just better to have this. We cannot assign it here, and we'll assign it here. This assign to vector bool and nodes are not visited yet. So I do the two DFSs, and now we'll calculate like the first component of the node. So it will be connected components of 0. So the CCS array is going to be the index of the connected component of the first in the first graph, and we'll have also the connected component in the second graph. So this will be here 1, and then the answer would be, we'll just add to the answer the size of the connected component 1, so size 0 connected component 1, and size of connected component 2. Cool. So answer is initially 0, and then we'll just output the answer. So what we will need is we will need the CCS, which will map nodes to connected components, and the size array, which will compute the size of the connected component. Also, we will keep two variables. So connected component count of, let's see, 1 and 0, and 2, which is 0. Also, it's not the best, like I code better than this. It's a little bit of pressure here. So I will do cc1 plus plus here, cc2 plus plus here. Okay, so what this will do is it will just visit all the nodes in graph 0 and visit all the nodes in graph 1 and populate size of this variable here. So let's also initialize the size array to vector of int of n 0, and let's initialize CCS to vector of int of n minus 1. And now we realize that the CCS array is actually the same as the vis array, so we can just remove this. So let's keep it the size and the connected component index, which is cool. Okay, and vis of 1 is like CCS of this is minus 1. So basically what I did is I did a little refactoring, because like we don't need the visited array anymore, because this CCS vector, if it's minus 1, it will just encode what we want. And now we have to just do the DFS function, hopefully. Int graph index, int node, and what do we need? Int connected component. And now, what do? We do CCS of GI of node equals CC, size of GI of CC plus equals 1. So we just include the node in the connected components, and now we just try to discover other vertices. So we go to all the neighbors, and if CCS of GI of vec is minus 1, DFS GI vec CC. This should be kind of it. Like, I'm a bit anxious to just compile it now and see what is going to happen, but let's just do this. Let's compile it. We have undeclared C. Why is that? Int ABC. Okay. Undeclared. Oh, I see. Oh well. This should have been a comma. Cool. It compiles all right. Let's see if it also works. 41, so it doesn't work. So what we can do now is, like, we can look at the code, but what I usually like to do is, for now, just output some values. Like, let's see what this size array looks like. Actually, first let's start with the CCS array. So CCS of 0 of y and CCS of 1 of I. Let's do plus 1 on everything because it looks better on screen. If and let's also do here. Cool. Now we will put this to an input so that we won't have to. Okay, so this is the graph, right? First node, it has, so in the one thing, it only has the first node is in the first component, which is what we want. And now we have 1. So the first component should contain nodes 1, 2, 7, 6, and 4 in the 1, 2, 7, 6, and 4, which is good. And the second component should like the other components should be their own vertices, which is good. Okay, and for the 0 thing, we should have 5, 2, 3 in the same component, and we have 1, 2, 3, 4, 5, 6, 7. Okay, 5, 2, 3. So this seems to be good. Now let's also show the size. So I plus 1. Okay, and this is like the connected component index, and then size of 0 of CCS of 0 of I, size of 1 of CCS of 1 of I. Cool. So we have size 1, size 5 should be good. Cool. Okay, for node 2, we should have size 3 and size 1, 2, 3, 4, 5. Okay, so this seems to be good, which might tell me that maybe I have some flaw in like my algorithm. Let's check it once again. So right now, what I would do right now is I would read the statement again and see if I misread something or if I have just some flaw in my thinking. Oh, I think I see what the problem is. So the actual problem is that we're also counting like the pair 2 2 in this scenario, because like the pair 2 2, actually you could think of the fact that it might actually be a valid path if you consider paths that have only one node. And in reality, for example, 1 1 is counted because 1 is in the ones component and it is also in the zeros component. So a very easy thing that we can do here is just do n's minus n and see if this works. That's also okay. So it seems to be working on the input case, which tells me that maybe I should just submit it right now. So let's do cat p1.cpp and copy this. This is just kind of the way that I do. I also know that I have some CRs, so I'll just delete them on the fly because, yeah. So let's see. We have this variable. This is long, so there is no problem of overflow, I guess. So this is all ints. Everything is an int. It should be just fine. So let's just submit it and see what happens. Surprises, surprises. Okay. Running on test 15. Running on test 26. So it seems to be working all right. We'll just give it like, I don't know, 10 more seconds so that we'll see the verdict. Hopefully it will not time out, but I think it shouldn't. Like it's basically linear solution. 34, 47. So I think you kind of get the idea. So let's recap for a bit. Like let's step out and recap for a bit. The first thing that I think is very important while trying to solve these problems and algorithmic problems in general is to kind of start with the statement and also look at the example. A lot of the times I do the bad thing of reading the statement kind of not very carefully, not analyzing the examples at all, and thinking of a solution, like trying to recognize the pattern of the problem and realize that I might have solved a similar problem in the past and just apply this. Okay, it got accepted, so it's fine. And realize that I have solved a similar problem in the past and just kind of blindly code that solution, while the fact might be that the solution could be like the actual solution could be easier or even like different completely because of something in the statement that is different. And usually examples might help you in this case. So I think like if I were to give an advice to someone, I know I don't follow it all the time, but if I were to give an advice to someone, I would say just try to go through the example. It might take you 1 extra minute or 2 extra minutes, but you might just save yourself the time of going down the wrong path because you haven't understood the statement correctly. So it's kind of like a trade-off, but I think like the thing that you lose is very minimal compared to what you would lose in like what you risk if you don't do this and you realize that, hey, I solved a different problem. So yeah, read the statement carefully and then try to kind of come up with like how, like here it's a counting problem, so we have to count pairs of vertices. How do these paths look? Like there's only zeros and then there's ones, and if like we with a bit of experience, I guess, you would kind of figure out that, hey, maybe the turning point from 0 to 1 is actually a very useful thing to kind of keep in mind as a pivot, kind of as the thing that I'm counting into. A lot of the counting problems just boil down to kind of, instead of counting the specific thing that the person tells you to count, you just count it in a different way. So you count it, you kind of accumulate the sum in a different way, and it works out a lot easier. A lot of the times you would see that as sort of like it's called kind of like contribution technique, in which instead of counting the specific thing that the author of the problem asks you to count, you just turn it around and realize that, hey, I can count for each vertex the number of paths that go through this vertex and stuff like that. And here it was important that for each path there is a unique vertex in which this happens. So it's not 0 and it's not more than 1. So it's only 1, which means that the number of paths correspond to just the sum over these special vertices. Okay, so I think this problem is kind of done. I am a better English speaker than Omnic. Thank you. Okay, so let's see what if you also have other tasks that I would look into. Okay, if you want to propose tasks, you can also propose them in the live chat. So I will be looking at the live chat kind of between problems and stuff like that. I won't be looking at it all the time, but if there's a suggestion about a problem that you think I would look into, just let me know here. It should be all right. Okay, so what have we done? We have done, they said EF, so I did a D from a Div2. So I kind of cheated it a little bit. Let's try a harder problem. Let's try should we do an F? I'm not so sure about that. I think we will do an E, and then we'll look into other problems here. There's also, like, I've seen that a lot of you have voted my test problem, which awesome. It's just outputting the sum of two integers, in case some of you don't know. Okay, let's try a different problem from the problem set. So another problem, let's go to a random page. Cool. Okay. Maximum balanced circle. Sounds like something. Can I solve any Div2 EDP problem? The thing is, I don't want to see, like, I don't want to know that it's a DP problem. So that would be the hard part. I would not know how to pick a DP problem because I don't know, like, I don't want to know if the problem is DP or not. If you want, you can propose to me a DP problem, but the problem is that if I will see your comment now, I will know that the problem is solved via dynamic programming. So it kind of breaks the point. So if you hadn't told me to solve DP problem and you would just have proposed the DP problem instead, it would have been a better approach. So just something to know. Okay, maximum balanced circle. It's a Div3. Let's go back. Let's try something. I don't know, something that is not Div3, I guess. Oh, we're getting to the harder problems. This is also solved by a lot of people. Let's see. Let's do some. This is solved by very few people, so I'm a bit anxious to just try that for now. We will be doing also like a harder problem, but not like in the beginning of the stream, because I want to build a little bit of courage for me for now. So this seems to be solved by 600 people, so it should be a harder problem. It's called minimal diameter forest. It's also with trees. Let's try something that doesn't have trees, I guess. Because like the last problem was with trees. Horseback riding. Okay, this seems to be. Should we try it? So let's see. Can we submit to this problem? What's with this? E contest 1000 what? 1090. What's this context? Oh, this seems to be Russia Open High School Programming Contest. Okay, fine. Let's see. So doesn't seem to be a particularly beautiful problem. Usually chess problems are not that great. So let's see. Do you want me to solve this problem? Pick random 2000 rating problem. Okay. So let's see. It's a well-known thing, chess is a sport. Somebody says that it's a boring problem. Might be. We can try something different. I was also not. I didn't feel that great to solve that problem, so I have no problem. So Sonya and Matrix Beauty solved by 400 people. Okay, let's try this one. This one is actually a Div2 E, so, and it seems to be different than the last one, which was with trees. This seems to be with some sort of strings, like a matrix of strings. So let's see. So just so you know, you can always copy the link and think about the problem yourself. Like have also the statement if you don't like it to look at it on the left hand side of the screen. So just something to know. Okay. Okay, so this just says that we have a regular matrix. So matrix. This actually this sounds like an interesting problem. So for those of you who don't know palindromes, I guess like most of the people watching the stream should have at least once encountered the notion of palindromes. The palindromes are like strings that are the same if reflected. So this is the same because like if you reverse the string, you also get ABA, CABA. So that's number of beautiful submatrices. Okay, so it's also a counting problem. A lot of counting problems. A lot of DP. Like you guys requested me DP problems. Okay, it might actually not be DP. So let's. So it seems like this is the most important statement of the task. So if we can independently reorder the characters in each row, not in columns, so that all rows and columns of this submatrix form palindromes. So what I'm thinking is that, like, for example, like if you have, so you have to count the number of beautiful submatrices. So obviously you would like a good thing that you want to think about right now is like what properties this submatrix has to have in order to be able to do that. So like what does it mean? Like have a better definition of a beautiful submatrix, because like this one is a little bit cryptic, like it's hard to work with. So yeah, so first is ABA. Why is it 4? Because in particular, like each element is itself a beautiful submatrix, and like the whole matrix, the whole 1x3 matrix is okay. So how would we do it? I think let's think about it for a little bit. How would we do it if we only have one row? So if we only have one row, we like one property that you would want to look into is like you would have to count how many subarrays can be formed, like if how many subarrays are beautiful. And beautiful means that you can reorder like them so that you will get a palindrome. So one property that you would have to obtain, let's see, online notes. Can we do this? Online notepad, no login required. So one property that a string has to have to become a palindrome, let's see, let's say we have A, C, B, B, S, S. So can this be reordered into a palindrome? Let's think about how we would reorder it into a palindrome. So let's say we start with A. The thing is, like, if we start with A in our reordering, we have to end with A because we want it to be a palindrome. So every time that we pick a starting character, we also have to pick it as the ending character. So if we pick A, we have to also put A here, and we're left with this. And now if we put B here, then we also have to put B here. So we end with this. And if we put S here, we also have to put S here. So we end with this, and then C can be put in the middle. So this seems to be like an example where you could reorder. Like the property that seems to be it, and I know it's it because it's not the first problem where I've seen like reordering letters to form palindromes kind of stuff. Like the property that you have to have is like each character should have count multiple of 2, so that if you put it in the first first letter, you also have to put it in the last, perhaps with one exception. Why is it one exception? Because like if total characters is an odd number, like you can put the C in the middle and still have the property of palindromes. So yeah, so this is like the basic property that we have to look into. So this is for rows. Now it's a bit interesting to think about what happens with columns, and I'm not really sure what's going on. Am I? Oh, wait, so this is the last problem. What happened here? And this should be it. Okay. So what happens when you have columns? And I will actually have to think about it for a little while. So how to check if a whole matrix is beautiful? We can reorder rows, and each row has to be a palindrome. So like some sort of algorithm like this should be applied. So in particular, like I'm thinking that if like the number of columns is odd, then we know which character to put in the middle. So that's determined, because like if the number of columns is odd, then obviously there is one character that has frequency odd, because you cannot have a sum of even numbers equals an odd number, and that character should be put in the middle. So it's kind of determined. What is not determined is whether or not here in this example you start with A or you start with B. So like a valid reordering would have also been this one that starts with B. And what does this give us? So you can reorder rows, form palindromes. Oh, I see. So the thing is, it seems like if I have, so let's say I have some other rows here, right, that are of equal length, and I put this B here. If I were to put AB here and BA here, the thing is I would also have to put an A here, because we want this to be palindrome. So like if I fix which character is here, I would also have to put it here. I would also have to put it here as the last character, and I would also have to put it here. And once we have done that, like the property is okay. Now, the question that arises here is whether or not it matters if I put A or B there. Because like if I put A here, and let's say I have like dots in the middle, and I decide to put A here. If I were to put B here, like I would also have to put B here, right? And B here and here. And it just seems that I would have to have like 2 B's in here and 2 B's in here for it to work. And it doesn't matter whether or not I put A here and B here, or B here and A here. Because like the 2 rows have kind of the same elements. So if I have 2 B's in here and I have 2 B's in here, it doesn't matter if I put them like somewhere around here or somewhere around here. The only thing that might matter is whether or not I put them in the middle or no. But putting them in the middle is, we've argued, that is kind of determined. So we know which things to put in like the middle cross in case there is one, in case like we have a matrix of 3 by 5, we have like some dot dot, something in the middle, and this is like the cross that I'm referring to. This would be the cross. I'm sorry that axes are not the same as dots in this notepad, something like that. So this is kind of the cross, and the cross doesn't exist if for example this is even. If this is even, then this doesn't exist, and like if this is even, then this doesn't exist. So it's kind of like a cross or a line or nothing at all. So these characters are actually determined, like you would know which to put where, and the only thing that is not determined is like these characters, but you can put them however you want. Okay, so now we kind of have a rough idea on how to see if a submatrix is beautiful, and I think a good thing is to go back to the problem and actually look at the restrictions. So n and m are up to 250. This is lower than usual restrictions for like a matrix problem. Like usually n and m would be 3000. So this is smaller, which means that the author of the problem allows us to do something like n cubed, I think, n times m times something. So something of order n cubed is allowed here. So what does that mean? It means that we can, in fact, iterate over two things. Like we could iterate over the 2 rows of the submatrix and compute the columns. And okay, let me think about this for a little bit. Also, it seems like there's also some property that I haven't used, but I kind of think that it's important. Let's also look at this matrix like a big matrix. Like if a big matrix is beautiful, something tells me that its inner submatrix has to also be beautiful. Is that always the case? So something like there is some substructure problem, like some substructure structure to this problem, so to speak. Is that true? Maybe not. So let's formalize. Each character has to have count. If I think about the first and the last, it has to have same count. Oh, I see. So first and last vectors have to be equal, like equal on all characters. Like so in order for a submatrix to be beautiful, if I have something here, like let's say these characters on the first row of the submatrix, then it seems to me like the last row should be the same thing modulo permutation. So it can have, for example, D here and S here and something like that, but it has to have the same frequency count for each character, because if it didn't, like you have to think that this column should be palindrome. Okay, so like if you have a character here, after reordering, you also have the same character here after reordering. So the frequency count of the rows should be the same. is that the only property that has to hold? Seems to me that it is. So like if this can be reordered into a palindrome, then we reorder it basically, and this has to equal this. So this has to be the same as this. So we reorder them in the same manner to obtain two equal strings, and then we just have to have, so the same thing has to happen also with this thing here, with what might be in here. So there is actually, after all, some substructure to the problem, right? Because like if we iterate over the first row and the last row, and we check only these, then the remaining thing that we have to check is that this submatrix is beautiful. So like the property that I'm looking seems to be like this. Submatrix is beautiful if and only if first row equals last row modulo permutation, and first row can be reordered into palindrome, and second to last, so row, form a beautiful submatrix. So this seems to be this seems to be necessary and also sufficient for a matrix to be beautiful, which means that we could actually compute. So like if we iterate over the first and the last row, it doesn't make sense to go up unless this, like if we fix like the middle row, it doesn't make sense to go up. It only makes sense to go up only until this thing holds. So what we can do, we can compute for each row a Boolean array. Okay, let's actually try to code this, and maybe it will be easier explained in the code. So also my great template that I have to write it by hand because yeah. Sync with. Okay. So first of all, the input. Let's get this thing out of the way. So two integers are read, and we have a vector of string. Let's call it mat of n. And for each row, we read it. So now we have the input read. And what I'm thinking is like for each row, compute whether or not, like for each row and pair of columns, we compute whether or not this row and these columns form like are valid palindrome. What we can do for this is just iterate over the rows. This is the row, and iterate over all the columns, like all the pairs of columns. K from J, K to M. Now we have row I and columns J through K. And what we do with this is we also keep a frequency array. Now the best way to keep a frequency array is to just, I guess, declare it here. We have how many? Okay, we have lowercase Latin letters, so 20. Let's do 30 because like I never know if it's 26 or 27 or whatever. And initially all of them are 0. So this will keep like the frequency. We would also have to keep the count of the, like how many elements are odd in order. So we want to kind of quickly compute whether or not this window can be reordered into a palindrome. So what we'll do, we'll just keep an odd count, which will just tell us how many elements in this frequency array are odd. It's just this. So now will be mat of I of k minus a. Cool. So now is something from 0 to 26. We just normalize it. And if freq of now is even, we increment odd count Else, if it's odd, we'll make it even. So we decrement old count. And we'll just do freak of now plus equals 1. Cool. So now we have adapted from basically from k minus 1 to k. Like we have also included the kth element, and we have the frequency array, which is dynamic, which dynamically keeps like each character how it is. And like if the frequency, if odd count is at most 1, then it means that this row can be reordered into palindrome. So we just say okay of I, j, k is true. And let's also declare it. It will be a vector, 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 bool, okay of n, vector, vector, bool of m, vector, bool of m, and initially doesn't matter because we'll populate all of them. Cool. So now we have the okay vector that just tells us if this can be reordered into a palindrome, because like the only and this has been computed in big O of n times m squared. So we're still in the time limit of the problem, which is good. We're still in like the goal complexity that we want to achieve. And now we would also want to check for it. We would also want to check like this thing, if it's equal to this thing or not. How to do this? Well, we kind of want to see if like this frequency array is the same. Like for ijk, keep the frequency array or some kind of hash of it. I haven't decided yet. But let's go back to the solution. So now we know that if this can be reordered into a palindrome for a row, if this can be reordered, and what I was thinking of doing is like iterate over the middle row and kind of add one row at a time. So let's see, what do we, let me have a little bit of a thought process. So we iterate over the middle row, and this middle row has to be a palindrome. Cool. Now I want to go up. This has to be equal. Obviously, n to the 4th solution shouldn't pass, right? 1.5 seconds, 250. So probably we want n cubed solution. Are we missing some observation here? Let's see. Have I read the problem statement good? Let's see. So the good thing is that this also gives a note. So the submetrics that are beautiful, obviously these ones. Also, matrices that consist of one element and the following. Beautiful. 1, 1, 2, 1. 2, 1. Okay. 1, 1, 1, 3. 3. Okay. Okay. 2, 1, 2, 3. Hmm. Okay, so what I'm thinking is that so after we have computed this seems to be a good thing to compute. Now what we could do is we could iterate over like the column, like split on the columns, keep like a window over the columns, and now compute some sort of hash of numbers for each column. Like for example, like if we fix that we're looking columns from here through here, we can just discard all of these elements and we have this kind of thing here, right? And also let's say this is a palindrome, let's suppose, and this is also a palindrome. We can compute some sort of hash number for this. So we have a hash of if this is a palindrome and if this can be reordered into a palindrome, or which should be the same of. And now we only have to compute, like if we're looking at this, we have to compute, if we iterate over the rows, we have to count the number of palindromes looking through the rows. And in order to do that, you can do it in big O of n squared, just iterate over the like have the palindrome and just expand it while it is a palindrome, or there is an algorithm that can do it in linear time, which is called the Manaher algorithm. Now, I'm thinking I'm thinking whether or not we actually need Manaher for this and hashes, but this is obviously a solution, and it might actually be the solution that I will be explaining. So the complexity would be 250 cubed. Let's see, Python 250 cubed. How much is it? So it seems to be 115 million. If we multiply it by 30, we get 468 million. This is not great, but why I did this is like to keep like the frequency array for each pairs, because maybe like I was thinking that maybe you don't need a hash, but thinking about it again, you might actually need hashes, which is obviously not great. I didn't want this to happen. But I don't know a better solution, so I think we will go with this one. So how to do this? We keep this OK array, right? And when we iterate through the columns, we also want to keep a hash of the frequency array. I'm actually thinking of like I'm literally thinking that maybe we don't need the hash, but we'll go with the hash anyhow. Anyways, okay, so we keep the frequency array and we'll just swap around the order of these two loops, because like we can do this if we does that make sense to swap around the order. If we do it like this and we compute it, okay. So yeah, let's actually do that. So we'll swap the order of these two for loops around. So we'll do for in j from 0 to m and for k from j to m. And now we have fixed like the window, right? And what we can do is we can damn, maybe it's not that great. Let's okay, we'll also keep a frac hash, whatever. So we do int 64 using int 64 long. Cool. Int 64 frac hash, which is initially 0. And what we'll do, we'll compute 30. We do rnd of I for rnd of I is rnd of I times rand max plus rand rnd. Cool. Now we have a random number for like each element in the frac array. And what I'm thinking is just like if we have now, we will just do freq hash plus equals rnd of now. So now we also have a hash over the frequency array, and this works. I will not go through all the logic why this is actually a good hash or like a unique hash. Maybe we also want to do something like rand times 0 in order to not be killed by some douchebags who like to anti-hash. Okay, and we will just also keep the number. We have OK of ajk equals true, else OK of ajk equals false. Good thing to do here. And also the number, so hash, let's say hash, whatever, because like hash might be actually a reserved word in C++. Cool. Boom, boom. In 64, in 64, in 64. I just figured that I may be missing an angle bracket here, and we'll call this hash. Okay, cool. So now we have computed the hash of the vector for each row and each column window, and now we'll just have to iterate through all the columns, all the pairs of the columns. K equals jk plus plus k. And now for we'll just do vector of int64 hashes. And so we want to only operate on things that okay, like for which okay is true. So we'll do if not okay of I jk, we'll just do hashes clear and continue. And now we know that okay is true, so we'll do hashes push back hash of I jk. So now we have the hashes. And before doing hashes dot clear, we will just update the answer. So ans plus equals count of hashes, which count is a function that I haven't written yet. It will just count the number of palindromic segments of an array. And we clear it, and if not, we push it back, and now ans plus equals count of hashes at the end. And this should be it. And let's do int 64, whatever, ans 0, and we'll just output the ends at the end. This seems to be okay. Now the only thing that we have to figure out is how to actually write this count function. So we will have a function that returns an int, which counts the number of so this counts the number of palindromic subsequences of v. And for the sake of this stream, I will be using, unfortunately, an algorithm from my library, like from my ACM notebook. So I'll just look for manaher.age. So manaher, if you can read like this commentary, it just outputs like two arrays, which says like the length. Let's actually we will actually need to read this. So the length of the longest palindromic centered in each position for parity 1, or between each pair of adjacent positions for parity 0. So if we output for 1 is like the odd palindromes, so it will give 0 the number to extend, 1 for this, 0 for this. So 1 is odd, 0 is even. Let's remember this while we paste this beautiful code. And we'll do for z. So this is like the oddity of the auto man equals manaher, and this operates on a string. Sadly, we will have to adapt it so that it will operate on like a vector of integers, and this might just be it. Let's actually look at this code. Does this use any char there? I don't. It doesn't seem to be it. So I just modified this from string to vector, and it should be okay. So we compute v with z, and now we have for z equals 0. So for man, in case you don't know Manaher, I don't want to teach you Manaher because like I'm not very great at Manaher. Also, like I wouldn't know to implement it from scratch, to be fair, but I can use it, so that's cool. And we have notebooks. So if z equals 0, we will have like odd things. So 1 here is good. So we want to have for odd things we have to add man of I. For like even things we have to add man of I. For odd things we have to add man of I plus 1. So if z equals 1, ans plus equals x plus 1, else ans plus equals x. Okay, and we'll just return the answer. That should be it. I mean, it's more or less a harder problem than the last one. I hope it compiles without any problem. Wow, awesome. It compiled on the first try. I'm not sure if that's a good thing or a bad thing. Okay, we have a signed integer overflow, which we won't mind because we are using hashes and like that's intended overflow. And 56. Okay, so anything else? I'm not sure. Maybe it's because I'm compiling with like overflow errors. No, it's actually okay. So we have a problem. Let's put some statements. Okay, so computed rand. This is like checkpoints to see where it's breaking, because like it seems to not. Computed hashes and okay. We want computed ends. And by the way, like if you have messages like this, I don't know if you know, but like you can just leave them on the source code. I know it's not a good practice. I don't do it, but like you can leave them. If there's a constant number of things, there shouldn't be any problem. So computed hashes and okay is all right. And like we have We have a problem on here, maybe? Okay, let's do it the old way, I guess. JK. So, okay, so 0, 0, 0, 0, 0, 1 is okay. What's happening here? Length error. I hate when I don't get errors that are meaningful. I don't know if you also hate it. So it's n times m times m. This is good. This is what we want. So 1 by 3 by 3, and this is ijk, so k from j, hashes, count of hashes. Maybe this is the problem. So what's happening here is that like I'm receiving a length error from a vector, and I'm not sure why I'm receiving that, because like I'm compiling with all sorts of warnings and like these things. If you see, it seems to be in some count. So maybe what's happening here is, I don't know, maybe this vector v is empty, and if v empty returns 0. I'm not sure, like I don't remember much of the code that I've written there and how it handles. So it seemed to be it. So like if v was empty, it was outputting the wrong answer, and now it's outputting the right answers. Cool. So this seems to be kind of good. I'm like, I don't think I want to give it some more examples. So we'll just submit it and see what happens. One thing that might happen is like we might get some wrong answer because of the hashes, or like some time limit exceeded, but I don't think so, because like the solution is obviously the right complexity. So if it's time limit exceeded, it might be because we're computing some hashes, and like that's some expensive things. So there might have been another CR somewhere here. So we only have count start and count end. So that should be it. Let's just submit it and see what happens. So usually, like even if this passes, usually like I wouldn't be happy with this solution because I don't like hashes and stuff like that, and I would still be looking at the editorial for this solution, because I am kind of expecting that there is an easier solution to this. Let's see what you guys are writing in the comments. Hello guys. Hello. Consider including a summary of the statement and current state of the solution in the notes and keeping them. Thanks for the feedback, Mihai. It's greatly appreciated. Okay. Cool. So there seem to be, okay, there seems to be a request for contest 660 problem E. So I might be doing that next. There's also, so this is running on test 30. This seems to be it. It seems to be okay. It usually, like, it's not every time that solution, like I submit solutions and they just pass without any problems. It seems to me that today is a good day, I guess. So let's also see what other problems are here. So there's this problem from Infoarena, which is a Romanian judge, and I also have the tasks translated into English, so there's no problem. But this particular problem I have solved, unfortunately, so I am not going to look at it. Nice idea, implementation for Div2 D. Okay, let's see. AtCoder problems. I think I'll just go through some problem. There's also a problem of, seems to be posted by me, but it's not actually posted by me. So this is not me. It's just somebody who posted it in my name. which is always awesome. Accepted 630 milliseconds when the time limit was what? Time limit was 1.5 seconds. It's not great, not terrible, as one would say. So, okay, so there is. So let's actually try a problem on Infoarena. Not sure. It might be a hard problem. So what we'll do with this is, like, I actually have a website in which I can translate this, like, any problem. It's like a website I made for myself, but one nice feature about it is that it translates problems from this particular judge. It takes a while to load for some reason. Maybe somebody is okay. Let's create. So we would want to go to something. Okay, I'll just add the problem here, because like that's one way of doing it. So here, adding the task, and it seems to be here. Oh, it seems to already be here. So okay, so is this the same thing? Yeah, it is the same thing. The only thing that it doesn't have explanation. So we'll see. So we have a tree with n vertices. Well, it's translated by Google Translate. So they ask for each value k between 1 and n minus 1, which is the number of subtrees of A for which the maximum degree of a node in the subtree is equal to k. A subtree is a connected subset of nodes and edges of tree A. The degree of node. Okay. Okay, so by the way, in case you want to take a look like at this statement for yourself, you can go to this link. Like you would want to go to this link, and unfortunately you would have to create an account, I think, to see this problem. Like I will fix it in future streams if that's the case. But this is like the link, or you can also go and see the Romanian version, which is not translated via Google Translate, so it should be better than this, at least in terms of understanding the statement. So what this problem is saying is that you have a tree with n vertices, and you want to calculate how many subtrees for each k from 1 to n minus 1, how many subtrees have maximum degree equal to k. So let's see. So let's draw the first tree. Do we have the drawing here inside here? No, we don't. Nobody minded. Okay. So 0, 1, 0, 2, 1, 3, 1, 4. And we have 4, 6, 2, 0. Cool. So in case you guys are wondering, let me just help you a little bit. I'll just show you the webcam. So this is the tree. Okay, so this is the tree in the statement, and this is the answer. So it seems to me that, like, for 4, why is it 4? Actually, why is it 4? That's a good question. Let's go back. So for each maximum degree of a node in the subtree is equal to k. Maximum degree is equal to k. Okay, so I see. So for example, the first value that you want to output is just n minus 1, because like the only way you can have maximum degree 1 is if you have just an edge. So the first thing is always n minus 1. Now the second thing seems the second thing seems to be holding, like you have a tree. So the second thing seems to be holding when you don't have degree 3. So only when you have these sort of things like paths. So if you choose your subtree to be a path, this would be the second value. And now the third value, like from then onwards, like the first thing is n-1, the first value you have to output. The second value you have to output is always n choose 2. So n choose 2. I guess this is the way you would write this. And now these we don't know how to compute yet. So the ones that are after 2. How we would approach this sort of problem? Let's actually go back to the webcam and have the statement as well. Let's see. I am actually not sure, but what I can see is that ni is up to 500, which means that, and 3.3 seconds on Infoarena means that we might be able to come up with some quadratic or even cubic solution to this. Maybe cubic solution is the best, or like n squared log n. That might also be something. I usually don't like just looking at the constraints. Like I think it's kind of cheating to look at the constraints and figure out the solution from that. But I like looking at the constraints to know how much I'm allowed to, like how optimized my solution should be. Like how much am I allowed to, I don't know, for example, if I'm allowed to use Floyd-Warshall algorithm for computing shortest paths instead of Dijkstra, which, like, for those who don't know, Floyd-Warshall algorithm is a very easy to write algorithm. It's just 3 nested for loops and you're done, and you've computed shortest path in graph. And that might be something that, if this were a shortest path problem, that I would be delighted to write 3 nested for loops instead of the whole Dijkstra algorithm with data structures. So that's why I'm kind of looking at the constraints. So n is up to 500. There's also subtasks. So for n up to 10, I think there is an easy solution where you just brute force all the subtrees. So for this kind of thing, there's like up to 2 to the n subtrees. So like where is the nodes? So for subtask 1, we have 2 to the n subtrees. So we just iterate and build every subtree and check like first that it's a valid subtree and then check its maximum degree. So we kind of have the solution, but we're looking for a polynomial solution. And it seems to be that this like 60% is actually n to the 4th or something like that, or n cubed log n. This doesn't seem like an easy problem, if you ask me. Okay. I'm thinking that what you could do is like you have to let's change it to webcam again. So let's go back to this actual drawing. So what I'm thinking is that you might be able, like for a subtree, in order to count it, you might be able to just count it where the top vertex is. So like if I want to count this subtree, I will count it at node 1. If I want to count, for example, this subtree, if I want to count this subtree, which is composed of 1 and 4, I will also count it. It's pretty hard to actually point to the right place. So if I have this subtree, I will also count it at 1. If I have, for example, I don't know, this subtree, which is composed of these nodes, I will count it at 0. So that's kind of like the first kind of approach that I would go through. Also, one thing that, let's go back to starting to get the hang of it, which is good. So also one thing that I'm noticing is that, so you want to calculate, you want to compute the number of subtrees for which the maximum degree is equal to k, so equal to k. One thing that's usually a good thing in this scenario is to maybe we'll use it, maybe we won't, but one thing that is useful is to relax this constraint. And what I mean by relaxing is, like, usually when you have to compute for each k something that is equal to k, maybe it's easier to compute for each k something that is up to k, up to or including k. So instead of computing, instead of constraining ourselves so that the maximum degree is equal to k, we could constrain ourselves that the maximum degree is at most k. Why is that easy? Why is that, like, easier? It's usually easier because, like, if you want to compute what I said, like the maximum degree is at most k, the constraint is actually that all nodes have to have degree at most k. Like, you won't have to also have the constraint, like, worry about the fact that there might be nodes that don't have degree k, so the maximum degree isn't actually k, it's k minus 1 or k minus 2. And there's like a trick that we'll do at the end to actually compute these values. It's a very easy trick. You just take one value here and subtract the ones before. So it's kind of like some sort of dynamic programming, but it's very easy, and it's easy to reason why it works. Nevertheless, okay. So strategies that I'm thinking about is iterating, like, over the root vertex of each connected component, and then compute something like dp of node of k. How many trees in the subtree of node are there, so such that all nodes inside are of degree at most k. Cool. Okay, let's try to see. Let's go to the implementation and see if there's going to be stuff that's going to be in the way. Usually, like, for me, I think my implementation speed is rather quick, and I don't have many problems, like, when I go from the thinking about the problem to implementation. So I usually, like, think of the problem 90% through it, and then start implementing and see if the other 10% just gets solved while implementing it, and I find out then. But you might find out that for your case, it might be actually better to have the idea very clearly in mind and then start implementing it. So I think this is something that everybody should just experience and see what you're most comfortable with. So we have t-tests, and we have to clean up after ourselves after each test, which is not ideal. We'll see how we'll do that. Okay, let's read the tree. Sin AB, graph of a minus 1 pushback. Some things to note here maybe is that I'm usually using STL a lot. The reason why is that for me, the fewer constants I have in the code, the fewer hard-coded constants I have in the code, the safer I feel. So so the fewer things that I have to check before submitting the solution is usually better. For me, at least, because a lot of the times I'm very let's say reckless, and I don't look through all the code beforehand before submitting. I don't look at the code very carefully. That's by the way, that's not a quality of mine. That's actually, like, that's not a good thing, right? That's one of the worst things that you can do in a contest where wrong submissions are heavily penalized. So yeah, one thing that I did to cope with this is I'm trying to use as little constants as possible. So I just prefer vectors. I will, however, sometimes use globals, although I'm not a fan of it. Usually when like there's DFS involved or stuff like that, I usually use it. Not all the time. it kind of depends on the problem and how I feel about solving it and how organized I want to be. So let's see. Let's actually try to do it without any globals, just to prove that a problem can be solved like this without any issues. So maybe assigning a vector of int 5 times might be a problem. What you can do is another thing is you could declare it and allocate memory here, for example, where it's like some sort of global scope, and just resize it and clear it after each iteration. Maybe we won't need this. So one thing, nodes are numbered from 0, so this is wrong code. Cool. It's good to catch these sort of minor bugs so that you won't waste time while debugging the task. So if I find something, I usually like modify it straight away, even though I have to go back through the code to modify it. Okay, so we have the graph and we want to compute dp of node of degree, maximum degree, how many subtrees. And for that we have to iterate over all vertices. And the thing is, oh, I see. So the thing is, like, if we have a subtree, which is back to webcam. So one potential pitfall is that when we want to count this as a thing that has maximum degree 2, so this will be counted as towards maximum degree 2. But if we want to propagate this tree to here, to count it here as well for maximum degree 2, it's not always the case, because this node has now degree 3 because it also has the parent edge. So how to fix that is, maybe we compute two different things, like we iterate over the root and we compute dp of I of j. We count the number of subtrees rooted at I, so that all nodes have degree at most j, and the root node has degree at most j minus 1. That's actually what we will do. And cool. We will try to figure out how this dp will work exactly in a minute, but for now we'll just do that. So yeah, let's actually keep, I changed my mind. We will just keep globals because it's easier. Okay, so we'll do graph assign n. By the way, this is like an easy way to just clear something. You just assign empty vectors n times. I don't know, maybe most of you don't know about this assign function. I use it a lot. So dp assign n, vector int of n, maximum degree is always less than n, and am I okay? Okay, let's go back to statement. It's better. Like, it's one thing that I have to remember constantly, is that when I code, I want the statement to be on the left and the code on the right. And there's a lot of times where I had this notepad that doesn't say anything, so I have to figure out a way to actually see the stream. That will be better in the future. Okay, so we assign n. So it's a 2-dimensional array, and we'll also keep the count in a global variable ans, which we'll assign to 0 at the beginning of our journey. Okay, cool. And now this is always a tree, so we'll just do some DFS that will start from node 0, and this will just compute the answer. Okay, so for I from 1 to n, ans of I, and some end line. Okay, so this ans is not an int anymore, it's a vector. So let's also assign it n and 0. Cool. So it's initialized with 0 and will accumulate the answers while we do the DFS traversal of the tree, because this seems to be the easiest way. So we will just write the DFS, which will compute all the k values. And now what I did is, like, I'm iterating through the child nodes in this graph, and obviously excluding the parent. That's why I'm keeping it. And we'll somehow call DFS of vec with parent node, and we'll somehow aggregate results here. How do we do that? How do we aggregate the results? Well, we can iterate through k, right? And say that all nodes have to have degree at most k, the root has degree at most k minus 1. So, like, if I want to iterate from, let's say, k, right? Because I said k through n plus plus k. Now we want all the child nodes to have degree at most k, the root to have degree at most k minus 1, and that's basically it. So we'll just keep all the values. Let's to aggregate, and should be here. We'll do it. Sorry, we'll do it at the end, because why not? So one thing that I want to do it straight away is just remove this check, because I don't like, in this case I'm iterating twice and I don't want this check twice. So what I sometimes do is do something like this. If par is not minus 1, I do graph node erase can I do this? I think I can just do erase par. How am I not remembering this? It's not the first time that I'm writing those lines. I guess maybe it needs an iterator. Let's be safe. Node begin, graph node, and par. But this is linear complexity. It doesn't matter because we do it only once, and it has complexity big O of adjacency list of node. So this is like big O of n, but we do it only once. So it's amortized big O of n, even though it may be big O of n at one step. It's big O of number of edges if we do this only once. So we erase basically the parent so that we keep only oriented edges through the child nodes. So we'll just do for all vex to egg. We append dp of vec of k. And now we have to somehow figure out a way that we combine these values. How would we combine these values? Is we kind of want the node to have at most k minus 1 such sons in order to compute dp. Let's say we first compute dp. We want this node to have at most k minus 1 such sons, and if we choose these k minus 1 sons, so the total answer would be kind of the product. So the total answer would be the product over all subsets of size at most k minus 1 of 2 egg of I. So this will be dp of node and k, which like k is fixed. So we have to kind of figure out a way to choose k minus 1 such things and have this. Now, okay, one thing that we can do in this scenario is we can just compute another dp over this. I'm thinking of in my mind if there's a better way of doing this, which also it might be or it might not. So how would this sort out? I have to pick k things. So we do another DP, which is big O of size squared. Is it fine to do this? I think it might be. Okay, so we iterate through k. This might actually be the time when it goes from big O of n squared complexity to big O of n cubed. Like I was wondering why this has 500, but I might have just got the answer right now, because it seems like you cannot compute this in big O of n squared time, but maybe I'm missing something. So back to the paper. Compute the p and the p of vec k, and we have to choose at most k minus 1 such things. So we have big O of size times k minus 1. Okay, so cool. There's actually a trick that might be involved in this like in optimization of this, which is certainly not a very beginner trick. Like it's more of an advanced trick that's pretty recent. When was this problem? What, 2015, 4 years ago. Interesting. Okay, so yeah, so now we have the 2 egg vector, and we could just kind of convolute it to sort of the answer. So let's do it. Let's do it like now, like this. So int now equals count of 2 egg, and we want k minus 1, at most k minus 1 things. So we want to take at most k minus 1. Is this okay? So we count how many subsets we can choose with this product, choosing only k minus 1, and this will be dp of at most k minus 1. This will be dp of node and k. So this is dp of node and k, and we will add to answer count 2 egg and k. Do we need to compute this twice? Maybe not. Maybe not. Maybe not. So we can do this. We can compute it once, I guess. Count 2 egg. Let's do this like this. For int I from 0. So this is like what I choose, right? This is what I choose, and choosing 0 has one way. We'll make sure that we do it like this. I equals k plus if I less than k, dp of node k plus equals now of I. If dp node k mod, dp node k mod, and ans plus equals now of I if ans kmod ans kmod. Cool. So now we do ends of k here, ends of k. Let's not forget this. So we propagate dp upwards up until k minus 1, because from k minus 1 we would also want to tie it up with its parent edge, and up until k we add it to the answer. So this should be it, kind of, and we only want to compute, like, to be able to see how to compute this toEgg function, which toEgg of, so int, we return vector of int count vector of int coefs. So what this will do is it will count, like, so in ret of I, it will be the sum of products of coefs of star or coef of j for all j in S, for all S in, let's see, for so products of X for X in S, for S subset in coefs of size I. So what I wrote and what this means. This means that I want to kind of combine the answers from the sums, right? In toEgg, I have the answers of the sums, which is like each node has to be degree at most k. And now we want to combine it, and we want to figure out, like, if we combine it into I elements, like, how many subtrees do I have? Well, we have to multiply how many we have in first, second, third through I. So this turns out to be sum of products of S. It's kind of more advanced combinatorics, let's say, but you would, like, if you don't know why this is, maybe I am wrong, but hopefully I'm not. But if I'm not wrong and you don't know what this is, you can come back later and try to figure it out for yourself on paper. It's not very, I mean, it's not the first combinatorics problem that you would want to solve this kind of problem. This is a more advanced combinatorics problem. So there goes, like, I just realized that this is the third problem about counting. We should find some different problems. You can think of different problem next. So ret of I, sum of products. So we will do dp, and let's do actually ret of coefs. How many can we have? We can have at most coef size, and initially it will all be 0, and ret of 0 will be 1, so that we're all okay. And now for each coef in coefs, we'll do some trick of updating this dp so that we don't mess it up. So we'll do int coef size j minus j. We'll do coef size -1, I guess. Anyhow, we can do it like this: for int I coef size plus I, do coefs of I, and then here we'll just iterate from I -1, actually from I. Okay, so now we have a subset of size j, right? And we want to see if we can, like, what happens if we add this coef. So we'll just do ret of j plus 1 plus equals ret of j. Ret of j times coef. And same trick. And then we'll just return ret. Cool. This is, by the way, this is like a very popular choice, or at least it used to be a very popular choice of modulo in Romania, because, like, I don't know how it it came up to be this kind of number. This is like a prime number. And what's, I guess, funny about it in the algorithm, like competitive programming community, but don't ask me, because like, is that it has this 666, so it's like the modulo of the devil or something like that. Anyhow, let's get back to it. So this seems to be doing the right thing. So it's computing like this answer, and now here it's propagating well. This, by the way, this might not be the end solution. Like, this might be actually slower than what we're allowed to do, but it seems that it's a solution that should at least pass, like, on correctness, right? So we say which we aggregate, and usually the bad thing about these DP problems, like the hard thing about these DP problems, is that you cannot reason very well about them just by outputting numbers. So you kind of have to actually look at the code to realize if you've been mistaken something. Okay, undeclared then. Where is it? This is from K, from 1 to N. I guess we can add N for now. So here it's not the case. Okay, so it compiles successfully. Let's paste this into an input file and run it from the input file, because I figured that there's going to be issues. Okay, so the DFS seems to be doing something bad, something really bad. Okay, what we can do is we can do LLDB a.out and do run and paste and see. Okay, so now how does that look? It has one value, K. Okay, so the thing is that we're iterating here up until K, but what we're returning this is just too few elements. So what we can do here is also and I now size, and this is correct. So it's correct to do this, only that this vector now would have zeros at the end, which we're not. Okay, so it's bad. Why is it bad? Well, there's some things that are being computed wrong, but you can see that, like, if we take 17, it's what I said in the beginning. Like, we're counting a different thing, but if we take 17 minus 17, this is actually 0. If we take 17 minus 15, this is actually 2. If we take 15 minus 1, this is actually 6. And maybe there's a 4 that we're not outputting, which we might want to be outputting. So in fact, kind of what we want to compute here seems, and it's actually, it should be the case, so it's explainable that it's like this. So we have to output the n's of I minus n's of I minus 1, and something like that. Now let's see what happens if we do this. So we have 9620. Why is it 9? Well, probably because we're also computing subtrees of size like, so we're not having anything on n's of 0. So what we can do as a quick fix is just set n's of 0 to be n. This is because, like, for the first answer, we're taking the difference between it and the number of trees that have only one node, like max degree 0, which actually exist. Like, they exist. They are the nodes themselves. Like, the nodes themselves, they have maximum degree 0. And we also added them. Like, we didn't compute n's of 0, so there was nothing to subtract from here, right? If we do n's of I minus n's of I minus 1. So right now, what we can do is just fix something quickly. Now, some things that might go wrong with this task right now. One thing is overflow. obviously. There might be some problems when I do these kinds of stuff. So one thing that's actually just by saying that overflow might be a problem, I just figured out that there is a bug here, and this should actually have a bin %kmod. So as you can see, it's very powerful to just ask yourselves these questions, like what could go wrong before submitting a task. This could have gone wrong, and this could have cost me 2 wrong submissions and 30 minutes of debugging. It got solved in 10 seconds just by asking a simple question. So very important. Just take a little bit of your time to actually figure out what can be wrong. And with experience, you'll kind of understand what can go wrong in different kinds of problems. For example, in counting problems, when you count modulo something, you might go wrong with this kind of thing. Now there might also be other problems here, like other places where I just don't wrap around correctly. Let's just quickly look. This seems to be okay. Okay, one more thing that I would actually want to do, and just to make sure, because it doesn't take me a lot, let's just give it one test when, like, on different examples. So n is from 1 to 500. Let's give it one test where n is 1. What happens? So with 1, it's not actually this format, right? Let's give it 5 tests, n is 1. What do we output? So is this fine? We have to output n minus 1 values. I guess we have to output 0 values, so I would say this is okay. So for 2, what happens if we do 2? 1, is that an okay solution? Yes, because we've argued that 1 is the number of edges. Let's also give it a chain. So for a chain, it seems to have zeros here because no subgraphs have maximum degree 3. So it seems to be working correctly. Now, one thing that I have to just alter on this solution is I have to add input and output files, because that's how this online judge works. So if stream scene off. Okay. Let's just check that it compiles all right, and then let's go to the task and actually try to submit. And surprise, surprise. Now, just as a disclaimer, what I figure is going to happen. I'm not sure about the complexity of the solution. I think the complexity is too high for this to pass. Maybe it's good enough, but my kind of rough estimation is that it's not going to pass. It's going to have time limit exceeded because of some ways I've coded it. Like I've coded some things that might have been coded better. Anyhow, let's see. So C++, live 1, and problem 3. And let's submit and see what happens. See what's going on. Refresh every second. Okay, it passed. So I was a bit lucky here. I think there's like an optimization that can be made here. Like, one thing that I was thinking about here is, like, that's usually a very, very, very cool trick that you can do. Here, instead of going up until n, you can go up until the size of the subtree. Is that super optimization? It actually is. We'll talk about it in just a minute. So let me just figure out if we have to do it like this or like this, like less than or equals or less than. Less than, that's fine. Less than is fine. Okay, and we'll just keep the size of the subtree here. Int sc equals 1, and this will return an int. This is just a very easy way to just keep track of, like, the size of the subtree. And now we'll just do this. And what I expect, like, my expectation is that these times would drop off very, very big, in a very big manner. Let's actually check that it's still all working correctly. So let's paste this into Grarbore. Okay. Okay, awesome. In case you didn't see, it's not working correctly. So something is missing. What is missing? Is anything different? So this is obviously up until, oh, I see. So let's see if the size, so the problem here is that you would actually want to, you would want to propagate, like add these values as well to n's of k. Like let me just think about it for a minute. So how do we aggregate these results here? So this now vector, oh, I see. We can just undo everything and do k up until n, and now let's also keep, like, if now size is less than, should I keep the last? Okay, last, whatever. So if k is less than size, let's do less than or equal size just to make sure. Now equals count of to ag, and this should in fact give some better complexity, should it? Well, we have n squared, and this is actually, so this is n cubed, right? This is n cubed, and we do it inside another for loop, so it's kind of something like n to the fourth, but I think it might be n cubed. Let's see. I actually wasn't surprised. I actually was surprised that this solution got 100 points. I think the test cases might be weak, this problem. So I will just do this. This shouldn't modify anything, but it should give us very big improvement to the performance of our algorithm. Let's see that it compiles. Okay, cool. Same thing. This might actually be better. Maybe it's not. Let's see. Okay, it's evaluating. So it's not that much different. I'm a little bit surprised that it's not much different. I thought that the difference would be one order of complexity. Let's not go there. Let's not go there too much. Maybe it actually improved the complexity, like asymptotically. Just this optimization. Maybe it didn't, but the thing is that we solved the problem. Now the complexity of this solution, I would expect it to be big O of n cubed. Why is it big O of n cubed? Why isn't it big O of n to the fourth? Because, like, so this is the task. Because, like, I'm iterating over node, right? So I'm doing this n times. Like this thing is done n times, right? This DFS is called n times, and now here is another for loop, so this is n squared, and now I call count, which also seems to do something that is big O of n squared. Why isn't it big O of n to the fourth? I will actually, let's see if somebody can like, if somebody figured it out in the comments. I'm actually, I would be, I would like to see if somebody actually figured out. So okay, meanwhile, we might, like, what is the time? It's so 2 hours have passed. I was thinking about something like this stream to be lasting something like 3 hours, around 3 hours. So we might have some time for another problem or two maybe. So do you guys have something in mind? But meanwhile, why is the complexity? Oh, actually, why does this solution work so fast? I posted a question for you in the chat in case somebody came. Like, in case you don't remember, to just have here. And this is like a little challenge. Why isn't it big O of n squared, or big O of n to the fourth? Or maybe it is, and it's just fast. Why did big O of n to the fourth apparent solution passed with 100 points? Please do problems from code forces. Do a Div2 VC for some context next time. You mean, I think you mean virtual participation, right? I guess so. It's both satanic and unlucky. It is. Okay. Well, if you want to propose if you want to propose a problem, I think now is the time. Count function amortizes to k times n squared. Why is that? Otherwise, what I am going to be looking into. So this is, I'm going to be probably looking into this problem next, because like it's very voted. It has 10 votes, and it's also an AtCoder problem. So if you think about it, it has like 10 plus 28, which is 38 votes. So it's actually, so the next problem is this, unless you want to you want to propose a different problem. Pair of nodes in the tree. It's kind of like that. I would say I think this is like there's an easier explanation to this. I think there's an easier way of saying why this solution might be better than big O of n to the fourth. So okay, I'm going to give you 1 more minute. If you want a specific problem, we'll do a specific problem. If not, we're going to be doing, remember, problem B from AtCoder regular contest 66. There's also this problem that we might try, 660 problem E. Okay, so time's up. Let's try to do AtCoder regular contest problem 66. Oh, this seems to be a math problem. What I like about the AtCoder problems is that they are, let's actually check the stream to see that you're actually seeing me. Are you seeing me? Okay, it's fine. So the thing that I like about AtCoder problems is that it's nice that they have very short statements, like everything is clear and concise. Sometimes, like lately, the problems are a lot of combinatorics and mathematics, and I'm not particularly great at combinatorics, so I don't enjoy solving them as much as other problems, I guess. So let's see. Another counting problem. This is going to be called a counting stream, like solving counting problems on first try. Even though like I I, I didn't sign up for that, but all of the problems are counting problems. What can you do? Okay. A XOR B equals U, A plus B equals V. XOR denotes the bitwise exclusive OR. In case you don't know what XOR is, you can just Google XOR. Operation, Wikipedia. Exclusive OR, it just tells you. Yeah, that's actually a very, I like this drawing very much. It's like exclusive OR is something that you would call in the set theory, you would call it symmetric difference. So it's like A minus B union B minus A. So it's like this picture. This picture is really good to remember. Really good, believe me. or don't. Okay. So XOR is just like it has a table, whatever. We'll not go through what XOR is after we've solved that hard problem of combinatorics. So I will, like, if you don't know what XOR is, you can just look it up. There's a lot of resources that explain it very thoroughly, and it's better than I could ever explain to you. Where is the problem? Okay, here it is. So A XOR B equals U, A plus B equals V. How would you solve this kind of problem? Well, one straightforward solution, let's say, is that you could just iterate over A and B, like for A for B, and see if the sum is V and the XOR is U. Obviously, that would be bad because N is big, right? So when you see constraints like this, it's usually you want to be looking at solutions like, for example, 10 to the 18, very big constraint. So I'm expecting a solution that would be something like polylog time. So log to some power of n. That should fit. Square root of n shouldn't fit. Like maybe with very, very much luck, because like square root of n is 10 to the 9, and I usually estimate like 200 million operations per second on like, so like 5 seconds for 10 to the 9, but that's not a great estimation. It very much depends on the problem that you're facing, things that are very, like, there are more subtle, like cache friendliness, stuff like that. So we're looking for we're trying to find out some sort of polylog solution, and we have, so A XOR B, A XOR B equals U, A plus B equals V. Okay, so let's see. A plus B equals A. So the thing is, like, there's some formula that I'm kind of putting on paper, is like something like this: A plus B equals A or B plus A and B. And there's like a formula that says A plus B equals A XOR B plus 2 times A and B. Now, why is this true? Like, how do I know these kinds of formulas? The thing is, like, it all relates to that beautiful graph that you see here. Like, XOR is this kind of red thing. If you think about A plus B is actually this plus what's in the middle. Like, it's this circle plus this circle. So it's also A or B would be the whole thing. So A plus B, that's like good mnemonics, I guess. A plus B is what's in the whole circle plus what's in the middle, right? And yeah, so there's like this relationship that relates adding to Xor, which like if Xor is this and adding is adding the whole circles, like if you add this and then this intersection twice, you actually get Xor. This actually, like you can see that, for example, a plus b minus a XOR b, so a plus b has to equal a XOR b modulo 2, which is always the case, because like if you want to compute the sum modulo 2, you can take the XOR and it's just take the XOR modulo 2. But yeah, this is kind of more powerful, and it all relates to this picture. Now the whole, like the why this works, it's kind of intuitive somehow. Like if we think about it, if we think about the binary representation, like the real reason why it works, let's say a is like this and b is like this. So you have some bits that are not matching, some that are matching, and some that so they can both be 0 or 0 and 1 or 1 and 1. If you take the XOR, it just takes all the bits that are different, right? So here it's 0 1 0 0 0 0 0 0 0 1, whatever. I might have put an extra 0 there, but that's not the whole point. So this is what the XOR is, and what's missing from the actual addition, if you think about it, it's this 1 plus 1, which actually goes as a 1 shifted to the left. So this 1 plus 1 actually contributes here. So if you think about it, it's like taking whichever bits are both 1 and then adding it shifted towards left with 1. So this is why this formula is like this. You can experiment it with it on paper and figure out. Now, is this useful? Maybe. I mean, the thing is, like, we have here a plus b, which is v, and a XOR b, which is u, right? So a plus b is actually v. So v equals u plus 2 times a and b. XOR answer, whatever, and okay. And numbers have to be, okay, a positive integer and pairs of integers, u and v. Okay, so a XOR b is u, a plus b is v. And we want to count the number of pairs that respect this. So, okay, so v minus u has to be divisible by 2. Now, can we always get pairs of integers? Can we also get a pair of integers, like if we have v, let's say we have 7 and 9, is there always a pair of integers that can and has to be if we have, let's say, 9 and 7, right? So we have a plus b equals 9, a XOR b equals 7. This is like an example. Is it always possible that oh god, okay, I just want to make sure that you can still hear me. My earbuds just ran out of battery. So did I try problem E from Context 660? No, but I'm going to try it next. So it's going to be just the next problem after this. So just give me a thumbs up or something if you can hear me, if the stream is still good.
Cool. Thanks. Okay, back to the problem. So, where were we? So let's say we have 9 and 7, so two arbitrary numbers. Is there always a pair of integers that have to have these properties? Let's see. So 2 times a and b has to be equal to 2, so a and b has to be equal to 1. What's the So if a and b equals to 1, so we have a and b equals to 1 and a plus b equals to 9 and a XOR b equals to 7. A XOR b. So a XOR b has to be some combinations of zeros and 1, and both of them, like the a and b, like both of them have to have some digits 1. And the thing is, it seems, thinking about like how this pattern should look like, is that a and b, so the bits of a and b have to be different from the bits of a XOR b. And if they're not different, the thing is, it's not possible, because you cannot have, like, a and b have to both have bit 1 at position I, and a XOR b has to have bit 1 at position I. So obviously if this is 1, then this all has to be 0. And now if we have this, then so if this, then the answer is some power of 2. I think 2 to the count bits of a XOR b. Okay. So back to the problem. There exist non-integers. So u and v, what did we figure out that it has to happen? So u and v have to have the same parity, and v minus u over 2 has to have different bits. Does that help a lot? Man, I don't like these bitwise problems. I don't like them at all. But this is idea 1, right? We can always go figure out some different idea. And all of them should be and u and v have to also be up until n. we might be able to just, so one thing that we might try to do here is, because like this is really quick, we can just output some pairs that are good and some pairs that are not. Now, or at least how many are there up until what? Because you have to take the sum, and sum is a bit problematic here. Bad task, very bad task. You have 1 here and 0 here. I'm thinking of doing some sort of dynamic programming on the digits of n. Okay, and the thing is, like, for this to work out, I need to somehow figure out what happens, like, if we fix bits from left to right, what happens if, so if for example you, so let's say we take bit 10. Let's say u in bit 10 is 1 and v is 1. So u10 is 1, v10 is 1. If this thing happens, it means that addition would yield it 1 and XOR yielded 1, which means that these things, which means so this means that there was no, how do we call it, propagation from below, and bits are different. Oh god, I don't like this problem. Okay, let's just do some safe stuff to check if we're not missing some stupid pattern. So for int u up until n, for int v up until n. Can we do it better? Should we do it better? Whatever, let's do it. So let's compute. We will just do some brute force approach to see if we're missing something. So okay, and u int v checks if are there a b such that a plus b equals u and a XOR b equals v. So if for int a can be 0, I guess so, right? Non-negative. Okay. Xor B something is, it's not letting me do my job. Okay, so we have 0, 1, 2, 3, 5, 7, 9, 10, 13, 16, 20. Yeah. Those numbers don't seem to be that random, to be fair. Let's compute DP. So this is just experimenting, because like I think there's a lot that you could feel, like there's a lot that you can see from these kinds of experimentations. Maybe not much here. Let's pump it up a little and see. We'll also do something. Okay, there seems to be some 1s, some 3s. I'm not the kind of guy that is like very good with patterns and stuff like that. So yeah. Anything that is particularly interesting about this? Let's output it in a different way. For int if I and 1. So now what I'm doing is I'm outputting the binary representation of I and how much I contributes to the sum. So this might not give me any insight at all, but I also have no idea, not much of an idea. Oops, let's do something that I forgot. Okay. So powers of 2, anything in particular about powers of 2? It seems to be 4, 5, this is 1, this is 4. Anything interesting about this? Two. This is 2. Okay, we'll try it. We'll try it some more on paper. So the difference has to be like this. And then what can we do for this sort of problems? Am I even outputting the right thing? that's actually a good question. And 3, 1, 2, 3. Am I outputting the right thing? Wait. Equals V. Okay, and let's just put actually dp of I as well here. Here, like this. So n equals 3. It seems that their answer is 5 and my answer is 3, which makes me think that something is wrong. Let's do v up until u, because like v cannot be, and clean this up a little bit. So from u is 0 here and 0 here. Now do we have the right answers? 5. Okay, finally we have the right answers. Good. 1 2 1 3 2 3 1 4. So I don't want to be cheating here and look up this like sequence on OAs, but I suppose a lot of people would do this at this point in time. So 2 3 1 2. This is 2 and this is also 2. Is this somehow related to something in the binary representation? I'm missing something. Okay, maybe it doesn't help to do a brute force approach, but I like in my opinion, a lot of the times, like when you have some problems in which a brute force approach is easy to write, you might try to write it and figure out if you can solve the problem just by looking at this. It seems to not be working. I'm thinking whether actually there can be multiple numbers for which UMV solves. So let's get back actually to this node. So v minus u has to be divisible by 2, has to be 0. The bits of a and b have to be different from the bits of a XOR b, which is obvious that the bits have to be different. So now the condition really is v minus u over 2 has different bits than a XOR b v. So if we think about fixing v, right, the thing is v minus u over 2. So v minus u over 2, this can, if we fix v minus u over 2, it can have all the values from 0 to v over 2, right? So you just have to count how many of these values from 0 to v over 2. So for a fixed v, count how many values less than v over 2 have bit mask have different bits set to 1. And now the thing is, like, if I'm fixing some bits on v, like think of it in terms of dp on prefix, something like that. So if n has a bit of 1, I say, hey, let's take the case where v has a bit of 0. Then these bits can be the same, can be however, and then v minus u over 2. So this thing that is less than v over 2 has to have different bits. So damn it, why am I solving this problem? So the thing is, up until p is up to 2 to the k, answer. What is answer? So okay, let's see. In the binary representation, MSBs are shifting to the right periodically. The LSBs are 0, 1 alternating. Yeah, like I think at this point a hint would be useful. So you can see a pattern in the binary representation. So this, are you referring? Oh, you're So any hints from you guys? Maybe you figured out something about the difference here. What I'm thinking is like I'm kind of going towards this idea where for a fixed v we count how many values. So this kind of formula. So for a fixed v, all the u's that are okay have, like, all the u's that need to be okay have this property set. So v minus u divided by 2 has to have different bits. So maybe, not even sure. Like I think I would be able to solve it in big O of n time, but n is very big here. Like in big O of n, I think I have a solution that would iterate over u, over like the sum, the one that is the sum, over v. It will iterate over v and then count how many values less than v over 2 have that property. And now can we do it faster? This ends with 0, and if we shift it by 2, I'm hoping it's not some sort of digit DP that's hard to write and hard to get right. Because I think I can figure out some sort of dynamic approach, dynamic programming thing that would count these, but it will be very cumbersome to write. And I'm thinking that maybe there's some formula that I'm missing. Okay, we will try a different problem, and we'll come back to this one if we have more time. So this counts as a loss for now. So let's it's kind of like, if I were in a contest, I would probably move on to a different problem. If I wouldn't, like, if I would have not much ideas on this one, I would just move on to another problem. In the meantime, you could think of it if it seems appealing, and if you like, if you have some ideas, we could share them. But I wanted to also look at some different problem, which is problem E from contest 660. So it was requested twice. Let's try it. So 660 problem E. Is it sum of also something to count? Is this the good, like, the proper problem? I think it is, because you said that it should be from an educational code forces round, so it seems to be it. Do I have submissions? No, so maybe, I hope I don't know the problem for a sequence. Yes. Number of distinct subsequences of A. How do you define a subsequence? That's the first thing. Unfortunately, it doesn't seem to be written anywhere. So, like, we have two different definitions of a subsequence. One is like when you take a contiguous interval and you have n squared of these, and one when you take just random subset, which is 2 to the n. I would suppose it is the second case in here, because usually, like, if you want to write the number of intervals, you would say the number of contiguous subsequences. So a sequence, number of distinct subsequences. Okay, so NM seems to be big. So what this problem seems to be asking us is, like, to simulate the following algorithm. We compute all the sets of length n with numbers from 1 to m. So all possible sets. And for each set, we take all the subsets. So it's like m to the n, right, to compute all the sets, and then to compute all the subsets, it's like 2 to the size of s. And then we want to see, like, to add each unique subset. So what I think happens here is something that's usually, like, when you have to count something over, like, you have to count over the set of all sequences, you have to count something, right? Some f of a, which is the number of distinct subsequences. Usually what's useful to think about is to think about, like, the subsequence. Think about in how many cases it's added. It's something called the contribution method. So it's I think Richter on Codeforces posted something like that, and I'm thinking this might be something very useful for this problem, where like if you want to compute a sum over something, like you can instead take each, I don't know, each small thing and see how it contributes to the big thing. Like here we could take all the supposedly sub-sequences, like all the subsequences, and calculate their contribution. So like for a given subsequence, like if we have, let's say subsequence is 1 3 1 4 5 1 4 6, we calculate how many times it is counted towards what? Towards the sum of f of a. So towards answer. Let's say, oh, I didn't want to do that. Oh god. I think there was a trick to reopen a last tab or something. Going through history. Okay. So how many times it's counted towards answer? And now this means that we have to count for each subsequence of this, in how many sets it is a subsequence. So the thing about this problem is that you have to make sure, so this is very important, make sure we don't count something multiple times. The idea would be for this subsequence that, for example, if we have 1 4 5 1 4 6 6 6, let's say we have this string, we must make sure that we don't count this one and this one as well. So one thing we can do to do that, like one trick that we can apply to this problem so that we don't count twice, is to make sure that, like, to restrict this statement so that we only count this subsequence once for a given big sequence. One thing that we can do is, for example, if this is 1, so if subsequence starts with 1, we make sure that we only take this one, like the first one that we encounter in a sequence. For example, if I have 1 1, let's say I have 1 2 3, so this is subsequence, and the big sequence is 1 1 2 3 2 3. So this is big sequence. In order to count this only once inside here, what we can do as a trick, we can make sure that we don't count it, like if we want to find this as a subsequence in this big sequence, we make sure that we find it using a very specific algorithm that finds it only once. One such algorithm is taking the first occurrence, like keeping a pointer here at this one, and when it matches, like going with here from left to right, and when it matches, for example this one, we make sure that, like, we match it here and we continue, so that the way we extract the subsequence is by taking each occurrence at each time. So this is a greedy algorithm to find out if a sequence contains a given subsequence. But the thing is, the greedy algorithm will only find one specific subsequence in the big sequence. So we can frame the problem as, for each subsequence, count the number of sequences for which the greedy algorithm yields this subsequence. So it's like we iterate, like we iterate over the subsequences in some way, and then and then we iterate kind of over the mask at which we find the greedy algorithm finds our subsequence. And what this mask tells us is that we don't have any ones. So like if we want to find out whether 1 to 3, like in how much 1 to 3 contributes to the sum, we can do something like iterate over all possible subsequences and add 1 for all sequences such that 1 to 3 is the output of the greedy algorithm on mask, so on a given mask. It's kind of hard to explain this, what I'm trying to do. So it's like we want to iterate over where it finds the 1, where it finds the 2, and where it finds the 3. And if we do that, then then that helps us because we don't count this thing twice. I hope it kind of makes sense. Hope it does in some sense. It's a bit hard to explain. So that means that here we shouldn't have any ones. So here is like no ones. Here is like no 2s. And here is like no 3s. We aren't allowed to have 3s in here. And if you think about it for a little bit, it's like a lot of the things are similar in here. For example, like if we fix the mask, so that there are, so for a subset, for a substring or subsequence of size k, there are n choose k masks possible. And for each mask, the thing is, here it has, let's say I fixed this to be no 1. Here you have m-1 choices of putting numbers here. So I can put anything but 1 in these spaces. In these spaces I can put anything but 2. So still m-1 choices, right? And also in this space I can only put m-1 thing. So what I want from you to notice in this case is that no matter how I pick this subsequence, like no matter how I pick where the algorithm would increase its pointer on this, where the greedy algorithm would increase, the thing is, like, the only constraints that I have to put on the big string is that there are no 1s here, there are no 2s here, and there are no 3s here. But in fact, it doesn't kind of matter where do I put them, because like I have the other boxes, let's say, that I haven't put numbers into, and on each other box I can only put m-1 things. So like the contribution of a mask of size k is so if I fix the mask, is actually m-1 times to the power of n minus k, no matter what the answer is. So like the idea is, like, if the contribution for a mask of size k is the same, it means that the contribution, so that means the contribution of all masks of size k is m-1 time to the power of n minus k, because this is for one mask, but all masks have the same contribution, because it doesn't matter which, like if I fix the numbers in here, it doesn't matter which, like if I fix these, it doesn't matter where the mask is, so it's times n choose k. And now, if you think about it, this is for a fixed substring, but we have to compute this over all substrings. But for a fixed substring, the contribution of all masks is the same. So this means that the contribution over all possible substrings of size k is this thing times the number of substrings of length k, which is m to the power of k. So I want to kind of look back to it and realize that like the only thing that we did is kind of switched to counting for each substring in how many super sequences of it. Super sequence means just a sequence for which this is a subsequence, like how many super sequences of it are there, but like the set of them. And in order to compute the set of them, I used this greedy algorithm. Actually, I realize now that there is something missing from here. There's also like one more step here, which is what is after I've outputted here, and this is actually important. This can be anything. So on this, after these three, this can be anything. So the contribution here is actually wrong. The contribution for one set actually depends. So it's like n choose k, right? So n choose, like depending on where the last element that we find is, we can multiply here by m instead of m minus 1. So here's like m minus 1 possible choices, here is m minus 1, but here there are m choices. So solution is not quite complete. So let's try to fix it somehow. If we iterate over last occurrence, what do we have? Well, if we iterate over last occurrence and we iterate over length, we have, let's say last occurrence is I, length is j. The contribution is last occurrence is I. So I choose j, yeah, times I minus j, and this is it's m minus 1 to the power of I times j times I minus j, and there are n minus I other things, right? So it should be n minus I other things, so it's m. And also there are m ways of choosing these things, so it's m to the power of j. So this is like the contribution of all strings of length j for which they occur at position I in our greedy thing. And this is now n squared. We're looking for a big O of n solution. J, I choose j. M minus 1 to the I minus j times m to the n minus I plus j. What might be useful here is to kind of separate I from j. So m to the n, it will be m minus 1 to the I times n m to the minus I. So it's something like, if I do this, maybe it's useful. M minus 1 to the I, m minus 1 over m to the I, times m minus 1 m over m minus 1 to the j. So what I'm doing is I'm just rewriting this, because like I have m minus 1 to the power of minus j, which times m to the j, which is m over m minus 1 to the j, and here I have m minus 1 to the I times m to the minus I, so it's m minus 1 over m to the minus I, and times m to the n, and this is the best I could do. And this thing is actually, so this is m minus 1. I'm not sure where I'm going with this, by the way, so I'm not sure. Okay, m minus m to the seems I minus j times m to the n. Does this help? Well, kind of. It kind of helps in the sense that this only depends on I. This seems to only depend on I minus j. So if you think about the fact that we're summing over I and j on this, we could actually sum, like we could fix this. This hints us that we could fix the difference I minus j, which the difference I minus j is actually the number of missed things, right? So the number of things that the algorithm skips. And now we only have I choose j times m to the n. So we have to sum over this. If we sum over this, if we iterate over I minus j, we have to get some sum of, so let's say d is I minus j. So we have to sum over d, something like d choose 0 plus d plus 1 choose 1 plus d plus 2 choose 2 plus whatever until n, I guess, times m minus 1 over m to the d times m to the n. This is just like I just fixed d, and I gave, imagine this is a sum, like sum over I, sum over j, right? And I fix this d, and then this thing starts to sum up. D choose 0 plus d plus 1 choose 1, and the thing is, like this is a pretty standard sum. This is like, where is the, if we do the magic Pascal triangle magic, the thing is like d over, so d choose 0 plus d plus 1 choose 1 plus everything. Can we, let me actually check that. Okay, so you can, nobody's complaining that they can see me, so they can hear me. So the thing is, like, we have to compute this kind of sum, and this sum is actually this element right here. Can I don't know if, so I don't have something to highlight. It might have been useful. So this element plus this element plus this element and so on, which is what we want to compute. It's like a sum over a diagonal. It sums up to be this element, like this here, 792. So all this sum is 792. Why is that? Like, the thing is, 792 is this plus this, and this is this plus this, and so on. So if 792 is the sum of the ones above it, and this is the sum of the ones above it, and this is the sum of the ones above it, and so on, then it turns out that 792 would, like, if you expand this and just continuously expand this, it will turn out to be sum of these values here. This is called like the I don't know, the golf club or something theorem of Pascal triangle, something like that. I'm not sure exactly. Maybe you could say in the comments how it's actually called. Okay, back to the problem. So it seems to me that it's just kind of like computing this sum. So what we want? We want d choose 0 plus d plus 1 choose 1 plus d plus 2 choose 2, and hopefully this is correct. Like there's no way of seeing if this is correct, and this would be actually, so this is sum up until d up until n, right? So this would be n choose 0. Let's see. So this plus this plus this plus this, and this is the nth row. This is the nth row of the Pascal's triangle, so it will be in the n plus 1 row, and the same thing. So hopefully, if I'm not mistaken, the last element here, up here, is n choose n minus d. So this means that the sum is n plus 1 choose n minus d. Okay, let's code it and see if it's actually right. So I think, by the way, I think this will be the last problem for today anyhow, so just so that you know. Okay, so to code this we will need probably, let's define the constant. Let's make sure it's the same. So k mod is 10 to the 9 plus 7, and now only integers here are nm, which other things we have to do, we have to compute binomial coefficients, and the way we can do that is by computing, like, let's make some functions. A plus if a this is just like addition, subtraction, modulo, so nothing fancy here. I just have to write them. I know this is not the usual way I do this. The usual way I do this is I just take my modulo. Actually, I think I can do that. Let's do mod int. Let's do it how I would do it in a contest, because that kind of makes sense. So this is like a very easy snippet. It's not optimized at all. It's just optimized for clarity and for shortness. So it's nothing fancy. So this is like mod int, whatever. Let's do factorials. We need n plus 1. 2 until n. Fact of I equals fact of I minus 1 times I. In fact n plus 1, 1. In fact of n equals in fact of n. This is like trick to compute factorials in big O of n complexity, basically. In fact of I equals I plus 1 times in fact of I plus 1. And I think I have to do it like this, the way I wrote it. Okay. Int n int k, this is just a function that returns n choose k. So fact of n times in fact of k times in fact of n minus k. And let's just check that we haven't done anything bad. We'll just okay. We'll just make sure that the Pascal's triangle is right, so that we don't waste precious time on that. So we have nm, and we just want to code this formula basically here. So I have to sum over d. Now d can be even 0. So for in d from 0 to, I hope that I didn't make any mistakes. Oh well, we'll see. So d is the number of failed things. So let's do up until n, I guess. Let's actually count the empty sequence separately. We'll see how. So we have at least one, like the subsequence has at least one element, and now we have to compute this. So d is 0 up until n. Okay, and int. So yeah, let's just forget about it. So mod int inf m equal inf m. Cool. And now we have to compute d choose whatever. So mod int res choose n plus 1 n minus d. And now we have to multiply it m minus 1 over m. So mod int n m, let's call it, I don't know, m minus 1 mod int inf m times m minus 1, and we do res times lgpow of mmd. I know I can keep the power here. I guess I could do that. Times pow equals pow times mm, and at the end we'd have to multiply it n, so to m to the n. So for ans plus res. That should kind of sort it out, although I'm not sure. Like there's this empty sequence that we haven't counted, so in order to count it, let's see, do we count the empty sequence? We do d choose 0, so this is the number of failed things. We do d choose 0. Is this I choose j here? I don't think it's I choose j. I think it's I minus 1 choose j minus 1. So sum over, oh god. So it's d minus 1 choose j I minus 1 choose j minus 1 times m minus 1 to the I minus j to the m to the j. That's fine, I think. Wait, m to the n minus I, m to the j, so that's fine. So it's just we have to compute I minus 1 choose j minus 1. So I can start 1, choose 0, d choose 0 plus d plus 1 choose 1 plus up on the last thing, this is the only n minus 1 choose n minus d minus 1. So this should be n that choose n minus d minus 1, and this should be fine. So this is the only difference, I think. A lot of combinatorics. I don't like combinatorics. Ans equals ans plus press. Okay. It seems to be it. This seems to be it. Now, the only thing that we haven't computed again is the contribution of the empty sequence. And the contribution of the empty sequence is just that we have to do ans equals 1 at the beginning. And I think this does the trick, because like in the end we multiply it by m times n, and the contribution of the empty sequence is m to the n, and so starting with ans equals 1 I think should be okay. In fact, little typo there. And let's see if this works. I'm going to be very proud of myself. It will probably not though. What do we have here? 43. Choose a light J. Oh, I see. Let's do up until n. 6 looks good. 14 looks good. The triangle also looks good. 174 looks good. Wow, that's good. That's good. That means that we can just put this here and problem is E, right? Okay, so at this point, I mean, modint cannot be wrong because I have used it before. The only things that can be wrong is some off by 1 errors here, but I think these were caught during like sample tests, so I think sample tests were good enough. I think we might submit it here and hope for the best. Let's see. Apparently I've tried D from this, not E though. I could see why I wouldn't try E. So so I've kind of accepted. So seems like I kind of washed my sins, as Romanians say, with the last problem. Hockey stick, yes, it's called the hockey stick theorem. Thanks. So I kind of washed my my sins with the second to last problem. I will be thinking, like, if you have an idea for the problem D from AtCoder regular contest, this is the one problem that we haven't managed to solve today. It's also like not one of my strengths, this kind of binary thing. What I would do is I would try to kind of stick with that idea of writing, like finding some relationship between sum and XOR, and do some sort of, so the idea would be to do some sort of digit dynamic programming on n that would compute this kind of answer. The only thing is that I don't know actually how to compute, like how to actually calculate it. I have tried writing some brute force that would do it. Actually, one last thing that I would very much like to do, because I am very, like, I'm curious, okay, and I hope you won't mind. I would just cheat a little bit just to see if I was right and you could actually go on OAs and find this sequence. Oh, not the right OAs, I guess. OAs.org, and look for. Okay, so yeah, I guess one thing that you could you could do to solve this problem is, it seems like these two sequences are the same. It seems that you, like, if you are in a contest like AtCoder is, like AtCoder regular contests are, you're allowed to use the internet. If you could use the internet, you could just search for this sequence. I didn't want to because I didn't want to cheat for this problem, but like one thing that you can do once you found this problem on oas.org, you could find out, like, there's formulas here. There's a lot, like, basically if you found it, then it's done. You have solved it, kind of. You just have to figure out where the actual formula is, and probably it's something around here. I'm not sure, like I cannot, I don't see it straight away. Apart from an initial 0 coincides with this. Maybe this would say a of 2k. There you go. There you go. A of 2k is 2 times a of k. This is very useful. This is very useful because that means that we can just code this. Like, let's code some quick solution just to show you how easy it is at this point. But of course it's cheating, right? It's cheating, for me at least. I mean, I feel like it's cheating anyhow. So if x equals, I don't know, if x equals 0, I guess, return 0. If x equals 1, return 1. And here, if mem of x, return mem, no, if mem count x, return mem of x. If x mod 2 is 0, return mem of x equals 2 times mem of x divided by 2 plus mem of x divided by 2 minus 1, no, plus 2 times count the x plus count x minus 1, else return mem of x. So I'm just basically coding this, just if you don't know. So mem of x, 2 times count the x over 2, count of x over 2, plus count of x plus 1 over 2. That should be it. I mean, map long mem. Oh, problems. We don't have map. Oh, we want this as well. Okay, it's compiled, and probably if I put it 3, it will, it put 5, put 4 for some reason. Let's see if this is not some off by 1 error. Let's put it 4, 5, 5, 8. Okay, so it's an off by 1 error. Whatever, we can just do this simple thing. Let's see if it's okay. 3, 5, 1, 4, 2, 2, and this big number. Damn it, do I have to count it? Oh, modulo. Okay, this is easy. But again, I don't count this problem as being solved anyhow. So it will probably, so that's what probably 90% of contestants would do if they were to receive this kind of problem in a contest. And that's why I don't like these kind of problems, because like if you have access to the internet, 90% of contestants would just write some DP and look it up on OAs, especially when the input to the problem is just 1n. So again, like the solution is there. Probably most of the people would do that. I didn't want to do that because it felt like cheating. But again, like this, if we were to think about what I would do in a contest, I would have searched it on OAs straight away. The first thing I would have done is search on OAs. If it is on OAs, the problem is done. If it's not, we have to actually think about it. So some wraparounds. Let's see if. So yeah, five problems solved today. I hope this was a good exercise for you. Like I hope it's been educational or interesting and something like that. I think I will be doing other streams as well. Not so let's one thing we can do. Okay. I think I will be doing other streams as well in the future. Not next Sunday, because next Sunday we will be on Petrozavodsk winter camp with our ACM team. We are doing it remote from Romania, but we are still like we still want to take all the 9 contests of Petrozavodsk. But after that, I think like if this goes well, if you think this was useful, if you think this is worth watching, I would very much like to continue these kinds of streams. I think it's useful for you because like so the difference that I see between these kind of stream where I solve problems that I haven't seen before and streams of people or like videos of people solving problems and explaining problems is that I think there's more to it than just the solution. Like for a problem, it's very important to kind of understand the reasoning and the way I come up with a solution to a problem. So I think a more important thing, and I think this will be like you will see this in the long run, is that for me it's more important to kind of have the right ideas and be kind of concise when coding and when reading statements and stuff like that. And this seems to me like some sort of a general skill. It's not so specifically. It's not like you know this algorithm or you don't. It's more like you actually, I think you don't have to know so many algorithms. You just like you don't have to know them by heart or like to try them. You just it's like a tool belt. Like you want to understand kind of to figure out which is the best tool to use in different scenarios. And that's kind of why I want to hold these streams, to kind of explain. And I kind of, I don't know, I'm missing a word here. I want to show you how you approach a problem. Like when you don't know anything about it beforehand, if you don't know that it's DP or it's greedy, or you like without, let's say, just iterating over all programming techniques, because yeah, that's also good. But I think it's also important to kind of understand the problem and try to solve it by getting the feel of it. And I think it's very hard to show this without actually doing it. Like when you know a problem beforehand and you explain it, it's usually a different dynamic. So you know the solution beforehand, you don't know which are the possible pitfalls. Like you cannot teach somebody how to figure out when they did the wrong step in their reasoning and stuff like that. So yeah, anyhow, hope you enjoyed this stream. I'm hoping that I will be making some more in the future. And see you guys next time, if there's going to be next time. I hope it will be. Thanks for joining me. I hope you had fun.